begin our, or continue our study of statistics just by learning some ways to describe our data. Okay, so these are, I guess we could call this descriptive statistics. And so here we are taking data, information that's been gathered, and we are going to have summaries for the data that we've gathered. So this is all from chapter 2. And if you think about a data set, you will have some kind of identifier. So let's say we went around, and we're not going to do this, but let's say we went around the classroom and we asked students, please tell me your name, your age, your height, your weight, your sex, your, I don't know what else, hair color. Age, height, and so a data set might have something like this, okay? Alright, and so on and so forth. Okay, so here I just have 2 entries in my data table, but maybe we've gathered data from everybody, and so I might have 40 lines or something. Okay, so in this case, or in our table, each row is a case or a subject. And each column is a variable. And we have 2 major types of variables. We have categorical variables and we have numeric variables. Categorical variables tell us to which category a subject belongs. Okay, so it tells us what type or what kind. Whereas numeric variables, they tell us how much or how many. So in our above example, which variables are numeric? Age, height, and weight. Okay, the first 3. And then the categorical ones would be sex and hair color. The book further divides categorical variables into nominal variables and ordinal variables. And it divides numeric variables into discrete versus continuous. Primary difference between ordinal categorical variables and nominal ones are that ordinal variables have a natural order, whereas these have no natural order. So, sex would be a nominal variable, okay? Because it would be equally valid to list the sex as male and then female, or female and then male. There's no natural order that makes sense of one over another. Same with hair color. We could list them in any order. Red, brown, black, blonde, white, gray, I don't know. Okay? There's no order that is required for hair color or sex. Whereas an ordinal variable would be something like small, medium, large. Okay, that it makes sense to have things in that order. Or strongly disagree, disagree, neutral, agree, strongly agree. That would be a natural ordering to a response that makes sense. Okay. A lot of things that we are accustomed to, like the order of our alphabet, is actually nominal. There's no reason why the letter B should come before the letter C. We are accustomed to it, and we've all learned the order of the alphabet, but there's no logical reason behind the ordering of the alphabet. Okay? Maybe there's a historical reason, a tradition, but in terms of trying to explain such a thing, I don't think it can be done. Or can it? Numeric variables, discrete and continuous. Discrete means only particular values are allowed, and continuous means basically you can have decimal points up to whatever level of precision that you want. So discrete would be, how many children do you have? And you would have to give me a whole number answer. Whereas your weight, if we had a very accurate scale, would give us continuous responses. Okay? It is possible for someone to weigh 172.13 pounds and someone else to weigh 172.136 pounds or something. Okay? It's just be slightly different depending on the accuracy of our scale. That's it. Okay. Or precision of our scale, I should say.
What was the definition of continuous?
The definition of
Or
continuous.
discrete you said was only particular values are allowed.
Yes.
What did you say for continuous?
Yes. Mine is kind of like a loose definition, being that decimal places up to any precision technically allowed. Okay. But what does the book say? A continuous variable is a numeric variable that is measured on a continuous scale. I don't know how helpful that is, but that's like looking up a word in the dictionary. What is contentment? The state of being content. Thank you. So we have that. Okay. Anyway. The main thing is you got to know the difference between a categorical variable and a numeric variable. Whether it's discrete or continuous, nominal or ordinal, that's of lesser importance. The categorical versus numeric, very important. If you cannot tell the difference between a categorical and numeric variable at the end of the class, you should not pass, okay? Frequency distributions. Okay, so when we have data gathered, all right, so this is starting off with a categorical variable, okay? So here's an example, okay, so maybe we've created a data table, and the example in the book is they went to a field of flowers, no, of 182 poinsettias, okay? We looked at 182 poinsettias? Poinsettia? I don't know. How do you pronounce that? Flower? Huh? Poinsettia? Okay. Poinsettia, well, this story is irrelevant, but I'll tell you anyway. I don't know why. My dog died the day after Christmas, and I blamed the poinsettia because she had eaten the poinsettia on Christmas Day. And so I thought that was the reason, and so I hated the flower after that. And then, but then I read online later, like, that it's actually not poisonous, so I don't even know what to think. But anyway, just to be on the safe side, don't let your dogs in your poinsettias, okay? Anyway. My dog died, it's not funny, okay. Alright, so anyway, we gathered data and then we said, okay, are the flowers red, pink, or white? And we've summarized them, okay? So we can summarize categorical variable with a frequency table. Categorical variable with a frequency table. Alright, and so here we would put the category and the frequency. And so the poinsettias can be red, pink, or white. And this is how many there were of each. Total of 182. Okay, so that's a frequency table. We can create something, we can add a column called relative frequency, or which is basically just a percentage, and we would get the percentage of each one. So we do 108 divided by 182 and get some number. 59%, 59.3, 34 divided by 182 is 18.7. And 22. So we have a frequency table or relative frequency table, and this can be represented visually with a bar chart. So on the vertical axis you would have frequency. 40, 60, 80, 100. So 108, somewhere around there. 34 would be somewhere around there. And 40, something like that. I guess if you used PowerPoint or something like that, you might make a pie chart, which is less preferred, because with a pie chart, the pie pieces for pink and white would be very similar and difficult to tell apart with the naked eye. Whereas with a bar chart, it's very easy to see that there are more white flowers than pink ones. Okay. I guess, all right, so is color of the flower nominal or ordinal? Nominal, I would say. I guess one could argue that there's a natural ordering of dark to light or light to dark or something like that. And I guess that would be valid, but if we treat this as ordinal, not ordinal, as nominal, then we could rearrange these columns to say pink, white, red, or pink, red, white, and the table would be equally valid. Okay, so I could just as equally have a table that looks like this. All right. I can rearrange the columns, and there's no no damage done. Okay. Rearrangement is allowed, especially for nominal variables. It's technically even allowed for ordinal ones, although maybe less preferred. Okay. On the other hand, we have numeric variables. And we can also create frequency tables for numeric variables. Okay. And so in this example, we looked at 36 different sows. These are pigs that, I guess, at 2 years old, no, a group of 36 2-year-old sows of the same breed were bred to Yorkshire Boars. So I guess at 2 years old, pigs can begin having children. So these, there were 36 sows, and we looked at how many piglets were born and how many piglets survived after to 21 days of age. Apparently, I know nothing about farm life, so apparently a lot of piglets die before 21 days of age. But we looked at a bunch, at 36 different litters of piglets, and we counted how many survived, and we summarized this with another frequency table. Okay, so this would be a numeric variable, which is the number of surviving piglets and this goes anywhere from 5 to 14. And we looked at, how many times did this happen? Okay, so there was one sow that had only 5 surviving piglets. There were no sows with 6. 2 with 7. 3, 9 with 10. 8, 5, 3, and 2. For a total of 36. Just a quick question here, and don't shout out the answer immediately because I want other students who might not get it as quickly to just think about it. So don't shout out your answer, but just think, in the actual data table where we've collected this data, how many rows do we have? All right, did you think of your answer? How many rows of data exist in the actual data table that we collected? That answer is, go ahead.
Infinite.
Okay, maybe I didn't explain this. I'm sorry?
36?
There's 36 rows, okay? So our data table has one line per case, right? So what are the cases in this data set? Each sow, each mother pig would be a case, all right? So if we just think about the data table itself, so I'm glad I asked this, because sometimes we lose sight of what our data looks like. In the data table, we would have the sow, and what would over here the variable be? Yeah, number of surviving piglets. And I would have, I don't know what pig names are, but we have Babette, Piggy, and I don't know, Pink. All right, whatever. And Babette had maybe 8 surviving piglets, and Piggy had 14, and Pink had 7. And so how many rows do I have in my table? I have 36 rows, right? One for each pig. And I would have a total of 36 numbers recorded here. Okay, nod if you're with me. Shake if you're not. Okay, so I got a shake here. Can you articulate what might be troubling?
So the numbers are those that added to 36 are the sows?
Okay. It's, okay. Let me,
Or their offspring?
Alright. Put this on hold here, okay? I'm going to just do a very small version of the table, and we will make a frequency table. And we'll come back to this in a moment here. Okay, so let me just show you how we make a frequency table from raw numeric data. Alright, so let's say let's do a simple example here, okay? And maybe we'll just go through the front row of students, front 2 rows. And if you don't mind sharing this information, just tell me how many siblings you have, okay? And if you don't want to answer truthfully, you don't have to, okay? And it doesn't matter, this is just for illustration. Just tell me your name, okay? So, we'll say your name and number of siblings. Okay, so what's your name?
Andrew?
Andrew. And how many siblings do you have?
1.
1. P, what, we'll do, okay, well, maybe I'll just say PA, sorry, no offense here, but just for the sake of time, just tell me 2 siblings, okay? And then next, Eric has 2 siblings.
Holly.
Holly has 1. Anne has 2.
Kai, 0.
Kai has 0.
Rebecca,
Rebecca,
4.
Nari.
3.
apologize if I spell your name incorrectly.
Carolyn, 2.
Caroline, 2, and then
Song,
1. Okay, so this is our raw data table. Okay, and we could finish this out by going through the entire classroom, but we will not. Okay, so this is my raw data table, and I'm going to summarize it into a frequency table. Okay, so number of siblings, this is a categorical or numeric variable. numeric, not a trick question. It's how many siblings do you have? And you either have 0, 1, 2, 3, 4, or more, or whatever. Okay. So over here, what I'm going to look at is the, here is going to be the number of siblings, and over here is the frequency that this has shown up. Okay. How many people did I interview? I think 10, right? 10 people total. So my frequency table, I'm going to start off with 0. And how often does the number 0 show up in my data set? Once. Okay, and then I go to the next number. How often does the number 1 show up? 3 times. What about the number 2? How often does that show up? 4 times. And the number 3? Once. And the number 4? 1. Okay. And so if I add this up, what do I get? 10. Okay. So all 10 people in my raw data set are represented in my frequency table. Okay. Is this good with everyone? Okay. So what we have over here is we don't have the raw data, but we just have the resulting frequency table. And I've got 36 sows represented here. And you can just imagine a raw data table where I had 36 rows, and I asked each, no, I didn't ask it, counted how many piglets from a sow's litter, whatever it's called, how many survived up to 21 days. And some, you know, most of them had 10 or 11 surviving, but some only had 5, or one only had 5, and 2 of them had 14 surviving, okay? Alright. Is that good? That's good. Okay, so anyway, we have, this is our frequency table that we've generated from the raw data, but we don't see the raw data in this case. And so this is one way to summarize the data. But oftentimes when you have something like this is not so intuitive. It doesn't, nothing pops out as striking or very interesting about a column of numbers. So we will often create a visualization, okay? And so one way is to create a dot plot. And with a dot plot, I put a dot for every cell. So how many dots would show up in my dot plot? 36, okay? And the horizontal axis is going to be the number of piglets surviving. So I have so the horizontal axis are the values that the variable can take on. And then I draw a dot for every case, or in this case, every pig that has that trait. So I had one pig that had 5 surviving piglets. I had 2 sows that had 7. So I'm going to draw 2 dots at 7. Same thing with 8, now I draw 3, and I can continue this on and complete my a dot plot that looks like so. Okay. And if you are like me, I would say the dot plot gives a better idea, or gives us a better picture of what our data looks like. Okay. And so, whereas it might not have been so obvious when we saw the numbers themselves, from here we can see what would you say approximately the average number of surviving piglets would be? Around 10. It seems around 10 or 11 piglets surviving is the average number of piglets that survive. Okay. We can change this. I should never do that. I'm tired of myself. I should never touch my mouth while teaching because my hands are covered in chalk. It's terrible. All right. Instead of a dot plot, I can create a histogram. And in this case, the histogram is going to be very, very similar to the dot plot. And rather than drawing dots, I have bars that represent that frequency, okay? So my tallest bar would have a height of 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And then across the horizontal axis, start at 5 and I go 6, 7, 8, 9, 10, 11, 12, 13, 14. And I would draw bars to represent. This one has 2, and you don't have to copy this into your notes unless you really want to, because I think the book has this exact picture. 12 at 5, 1, 2, 3, 4, 5. Something like that. Something like that, okay? And this is a histogram rather than a dot plot. Okay. The advantage of a histogram, though, okay, or why would we make a histogram not a dot plot? Okay, well, if you have a whole bunch of dots, let's say you didn't look at 36 sows, but I don't know, you went to Farmer John's farm and they had 3,000, or I don't know how many pigs they had. You don't want to look at a graph with 3,000 dots. But having bars might be easier, okay? You can also change the width of the bars. And, in this case, it's not as necessary, but we could. I could create bins, and the bins can be any size you specify, but let's say I specified my bins to be 2 wide, meaning I would include 2 numbers in each bin. So my first bin would be including sows that had 5 or 6 surviving, and then the second bin would be 7 or 8, 9 or 10, 11 or 12, 13 or 14. And so what is the frequency of that? So how many sows had 5 or 6 piglets survive?
1.
1. How many sows had 7 or 8 survive? 5. Okay. Is it anybody having trouble seeing where I'm getting 1 and 5? We're all good there. Okay. So then if I continue this on for 9, 7, oh gosh, I can't read this thing. 9 and 10, I think is 12, and then 11 and 12 would be 13 and 5. Is that correct? Okay, and then I could make a histogram with this. Okay, and I would have to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And 5. We would draw bars at the left edge of each thing, and I would have 1, 5, 12, 13, and 5. Okay. And so here is my histogram where I've changed the bin width to a width of 2. So both of these histograms have the same underlying data, but they do look somewhat different. And that is because we've changed the bin width on those. Yes?
What's the difference between a histogram and a bar chart?
So a bar chart is for categorical data, and a histogram is for numeric data. In a bar chart, what goes across the bottom axis? So in the poinsettia example, what went across the bottom axis?
Colors.
The colors, okay? So in a bar chart, the thing that goes across the bottom axis are the names of the categories, or the labels of the categories, okay? In a histogram, what goes across the bottom axis? No, frequencies. The values of the variable, okay? So the numeric variable, we don't have the raw data table, but the numeric variable was how many pigs survived, okay? And so the values of the variable go across the bottom axis. On a bar chart, you can rearrange those bars, and it's fine. You cannot rearrange the numbers on a number line, okay? You would have bad problems if we tried to say 5 came after 9, okay? You have to leave the bars, or leave these numbers in order. And so in a histogram, you cannot rearrange the order of the bars. In a stylistic point, histograms generally have no gaps between the bars, where bar charts generally do. But that's more stylistic than functional. So the horizontal axis in a histogram are numbers, and they are the numbers that that variable takes on, that the numeric variable takes on. The vertical axis is what? The frequency. The vertical axis is the frequency. So both in bar charts and histograms, the vertical axis is frequency, meaning how often did that value, or did that, I guess value, appear in your data? How often did the color or the value red show up in the data? That's represented by the height of the bar. How often did a value between 9 and 11 show up in your data set? That's represented by this bar with a height of 12. Are we feeling good about histograms? Okay, so again, if you're good, nod your head and smile. If you're not, then you can shake your head. I'm only getting some nods here, so maybe we're not as comfortable as I would want you to be. Okay, well, perhaps there, yes?
Just one more time, so on histogram, the x-axis is
It's not the,
It's the values. Okay, these are values that our numeric variable takes on. So what is, in this case, what is the numeric variable that we are looking at? Number of piglets surviving, right? So even though we don't have the raw data table, you could imagine a raw data table with 36 entries, each one corresponding to a different sow, and how many piglets survived. And so in that column of how many piglets survived, we could see numbers anywhere, technically from 0 to, I don't know, 30 or something. But in our data, only the numbers between 5 and 14 showed up. And so when we create our histogram or dot plot, the horizontal axis goes from 5 to 14. And I'm putting a dot for each sow that had that number. Okay? So there was one sow that had 5 piglets survive. She's represented here and also here in this histogram. getting some smiles and some hesitant looks. I'm going to go with my gut and keep going. And if you have any questions, please don't hesitate to raise your hand and ask, okay? And if you say, well, can you go back to this, that's also okay. And if I feel like I can't answer that question, then I will say maybe I'll answer that later or something. But fear not. Okay, so we have a histogram like this, right? And you can imagine, perhaps I have another histogram. That looks like this, okay? And instead of having to draw out histograms with all of these bars, I might just represent the overall shape of a histogram with a curve. Is that okay? Okay, and then so using curves, I can talk about the shapes that a histogram might have, or in essence, the shapes that the data itself has. Okay. Before I move on, what kind of variable am I looking at here? A numeric variable. Okay, a numeric variable. What does this represent? So, whatever my numeric variable is, whether it's height, weight, number of piglets surviving, this piece over here represents an individual, or maybe a few individuals, with a high value in the numeric variable. But is it common to have this high value? No, and that's why the bar here is low. What about this one? Okay, so it's very common, okay, because the bar is high, and the value is neither very high nor very low. It's actually kind of in the middle. Over here is an individual or a few individuals with a very low value in the numeric variable, but also not very common because the bar is very low. Maybe I'll write that, okay? So low value in numeric variable, not common, okay, indicated by low height of bar. Opposite over here, high value, not common. This would be quote middle value, very common. Is that good? You understand that? Okay, and so that is represented by this curve right here. And we would call this shape. So when we're talking about shapes, there's two aspects of shape that we want to talk about. One is how many peaks, and the other is the symmetry. Okay, so this one has one peak, so we call it unimodal, and it's symmetric. Okay, meaning I can stick kind of a mirror down the middle, and both the left and the right hand sides look pretty much the same. Okay, so with a symmetric distribution, whatever you have as your middle, okay, that means if you go above for the numeric variable. However, how common it is to be this high above, it's about equally common to be that far below. Okay. Unimodal means there's one peak. So let's look at a few other unimodal ones that aren't symmetric. Okay, this thing, how many peaks?
One.
One peak, still unimodal. This is skewed right. Okay, and that's because this is known as a